This is a chemical kinetics podcast in which the pressure dependence of rates and the Lindemann approximation will be discussed. Reactions depend on collisions. Some of the translational energy involved in collisions can be transferred to the internal energy of a molecule, instigating a bond breaking or making. Remember in the discussion of bimolecular collision theory, for a reaction to occur, a certain amount of energy must be present. One type of collision is when the colliding molecules rearrange their bonds among themselves. Another type of collision is when an energy is transferred to the molecule by the surrounding molecules, represented generically by M. This collision puts the molecule in an excited state, which leads to the change in bonding. The difference is that the molecule that hitting the molecule does not change. It just transferred some of its energy. Since the molecule transferring the energy does not change, and since, for example, many molecules can have this effect, the molecule is represented by a generic M. Unimolecular decomposition is only possible if enough energy is available to break the bond. This energy is provided by collisions with a generic set of molecules M. The Lindemann model is based on the production of an intermediate excited state of a molecule, here seen as A star, produced by the collision with a generic set of molecules denoted by M. This can be represented by three reactions: production of activated species in its reverse, and the activated species going to products. From the system of three reactions, the rate of production of the activated species can be written. Since this is an intermediate species, and its decay is very fast, we can assume that the species is in quasi-steady state. And from that, we can derive an algebraic expression for the concentration of the activated species, shown here. This can be substituted back into the equation for the production of the products of the species. And here we have basically an expression with K's times the concentration of A and M over the concentration of the reverse times M plus Ku. The Lindemann model recognizes that some reaction rates have a pressure dependence, specifically the dependence shown on the graph. At high pressure, the rate goes asymptotically to a constant, K infinity. At low pressure, the rate is a constant slope, dependent on the reactant. Lindemann model recognizes that some kinetic relationships cannot be represented by a single rate constant. The following is a derivation of some of the extra Lindemann coefficients. At low pressure, the concentration of the collision partners is small, and the conversion to products dominates. So the term with M disappears in the denominator, leaving the expression K times A times B, meaning second-order kinetics. This produces the slope of the line dependent on M in the graph. At high pressure, the M term is larger, and the reverse dominates. Thus the term M in the denominator dominates, leaving first-order kinetics in the final expression. This product leads to the flat fall-off behavior shown in the graph. The two fall-off coefficients can be derived experimentally by plotting the log of the species versus log of the rate constant.